Hello, math fans. I'm Dr. Andy Lovelace, coming here to talk about the melting of a snowball. This is an example that comes up when I teach differential equations, our Math 207 course. I always like it as an example that leads to what we call a nonlinear differential equation, gives us the chance to talk about existence and uniqueness. But I've never done an experiment with it. And we recently had some snow days, and so I tried. I had to get a team together. That team involved Kelsey Plum and Wally and Eva. They came to watch the video. I know I'm losing it. There's someone in the background that's hiding right now. But did several experiments, had my kids help me, made mistakes along the way, found that things don't fit perfectly, but it's still a good model. And so I'm going to do a few different videos. The first one's just going to be some visuals for anybody that's interested in the melting of a snowball and what it looks like and some of the things we consider. There's this main assumption. If you can find this in a Calculus 1 course on a section on related rates. You can find this in a Calculus 2 course when you're doing the beginnings of differential equations. You'll find it in Math 207. So this is something that appears as an example in many things. I've just never done a physical experiment. So I hope you find it interesting. So I'll do a video on kind of intros and visuals. If that's interesting to you, please like it or subscribe it or let me know something in the comments. I want to know this is reaching someone. And then I will do the differential equations and solving. And I'll talk about the differential equation for the volume and the differential equation for the radius and how to convert between them, and that'll involve related rates and things we do in Math 124, 5, and 6, and 207. And then I'll talk about slope fields in theory, and that's when I get to talk about existence and uniqueness, which often students think of as this real theoretical thing, but here it applies to a melting snowball. And it has meaning, it has significance here, and so I'll finish with that discussion. So I'm planning, this is video 1, that there will be 3. Let me know if it's of interest. I thought I would finish this by showing these visuals, and you can watch the snowball melt. Other things I got to use was spherical coordinates, because that's the way that makes this look the nicest. But so I did a model based off of what I saw in this experiment of a shrinking snowball. So here's my model. We'll see how that video goes. And my computer's set up. I'm trying to get a new computer this week. That's why your support is helpful to let me know I'm not wasting my money to buy a new computer and better visuals. So there's my model for the melting snowball. Okay. Let's pause that. And here's the actual what we saw. So I packed some snow. We tried to measure it. I wish I'd have put the measuring stick in a different spot. We set a few things around here. Some student gave me this. I did not buy this for myself, about being a super cool math teacher. I think it's an oxymoron. But I did want to include Wally and Eva, and then whoever's hiding back there, who's one of our favorites. So here we go. Let's watch this go. I've been having trouble with it buffering, so hopefully we can see it. I put a clock there. I had to speed it up to like 16 times speed, or else we'd be sitting here for many hours to watch this. But you can see it's melting. So, when you're just standing there, you can't see it with the naked eye, but if you put it over quite a bit of time, this is what you see. This is the fastest I can make it go. And I need better editing software. So there you go. What I found was that it loses about a half an inch of diameter an hour. Now, it wasn't precise. The model wasn't perfect. You can see I jumped around a little bit, so I need practice with my ability to do some of those things. But let's let it go again. And this time I'll hit here. Okay, we're going to send this one going. We're going to send this one going. See if they can be side by side. I've unfortunately noticed that my video playback speed slows down when I'm trying to show more thing than once. So I've had hard time getting them to show together. That's why I'm going to get a nicer computer here in the next week, so I'm not spending so much time with processing. You shouldn't try to do these things with computers that are 10 years old, is what I'm discovering. So there you go. Kind of a little bit of a visual. As you saw, not a perfect fit there, but my timing. I just wanted you to see what we're after. So in the follow-up videos, what I will do is talk about the typical model. What I actually did was I measured, so there's a few snapshots from that. Kind of what happened each hour. So it's a big snowball I had. I also did several experiments before this one. But Stitch said we needed to do one more with a timer, and he was right. So in this, what I'll talk about is just setup. How would I study such a thing? And there are several things like this in differential equations. We could do experiments every day on different things. My goal here is to see this physical thing. So we observe that it appears to lose about a half an inch of diameter per hour. Now there's some problems like it melts through. There's an observation that when there's more surface area, it melts faster. You've experienced this with like crushed ice. You crush ice, it makes it so there's a lot more exposed surface area and it melts faster than if you have a chunk of ice, because less of the surface, the material is exposed. So I will, in a follow-up video, talk about the differential equation. I just thought I'd give a little preview. So ultimately we have this statement that says it melts, basically loses volume, and that's what this represents. As you do this in Math 124 and Math 125, this is the change in volume. That it's proportional to the surface area, some percentage of the surface area. Now, interesting, in doing a bunch of these experiments, I don't know if that's the perfect model. There might be some adjustments needed. But there's this thing, we think of it like a bank account, like what percentage are you losing every hour or every minute, depending on your units? Are you losing 30% of the volume? Are you losing 10%? That's how we think about that. What percentage? But they say it's some percentage of the surface area. So then right here we have the surface area. But unfortunately, we have three things. All these three things are changing. The radius, the volume, and the surface area. So we would like to not have three variables in the problem. One variable here, two variables the time, and three is the surface area. So we do some rearranging. We say, well, the volume, if this were to stay a perfect sphere, which we see it wasn't, but the volume is 4/3 pi times the radius cubed. But the radius is also changing, right? So we have several things changing at the same time. And that's what you study in Math 124 when you talk about related rates. How do we handle these situations when many things are changing at the same time? And this is for Math 124 students. You may know that if you in that situation where you're not thinking of any of these as constants, you're thinking all of these as changing. The V is changing, the R is changing. You can differentiate directly. And say something. Bring the 3 down, 4 pi r squared. Now that's different than like partial differentiation or something else. In this situation, I talk a lot in Calculus 3 about the role of your variables. But in this situation, the role of our variables is they're all changing. Nothing is constant. So anyways, this is stuff you do in Math 124, and this is valuable here. In fact, there's probably a question like this in Math 124, but you stop there and you don't go any further with it. The place you end up using it is in differential equations. The surface area of a sphere is 4 pi r squared. Now, there's an interesting observation that that's the derivative of this with respect to r. There's a reason for that. If you think about a sphere, and you take the derivative and talk about how it changes, if you make the sphere slightly smaller and then think about how the volume has changed, that has to do with the surface area on the outer edge, the surface area times the thickness. So there's a reason that happens. It happens in higher dimensions. If you're talking about hyperspheres, you always have the surface area of a hypersphere is the derivative of the volume. I only know that because I had a student study how to cut pancakes in higher dimensions, and we came across that fact. But that's a video for another day. Okay, so what it says here is that this needs to be 4 pi r squared. That's still a problem because there's still 3 variables. So what we can do is one of two things. We can convert it all to r, which is the easier way, or we can convert it all to v. So in the next video, I will talk about what if we do it in terms of v. What if we decide we want to study the volume? And that leads to some interesting things. Even though it's not the cleanest way to do it, it leads to a bunch of interesting questions. And so I'm going to do that. But then we also talk about in terms of r. Now they both answer the same question. It just happens to be nicer in terms of r. And that illustrates some of the things, some of the usefulness of some of those related rates. So the in terms of r piece says, well, this is the same as this, and so we can use related rates and simplify it dramatically, and we get a really nice expression of dr dt equals negative k. And that tells us that the assumption about it melts at a rate proportional to its surface area predicts that the radius will change at a constant rate. And you might say that's diameter, but the radius changes. So what I found in this experiment is the radius was changing by about 1/4 of an inch an hour. So that was roughly correct. Not as accurate as I thought it would be, but anyways. The volume one is messier because you're going to have to get rid of r. In order to get rid of r, you'll have to solve for r in terms of v. So if you solve this for r, which I'll do in my next video, and plug it in, then you get a differential equation for v. That's a nonlinear differential equation, which is nice for us to experiment with because a lot of the examples we do that use just very simple assumptions are linear, and so we don't get this behavior that I want to talk about. Nonlinear differential equations often have issues about solutions not being unique or not existing. That doesn't mean they're bad. It just means we need to be aware of that if we're solving. Okay? And I am no expert. You got to take a course in Math 207. I've taught that one before, but take courses beyond it if you want to know the theory more. My goal here is just to give you a little taste of some of the things you're going to encounter if you go on to that course, and that the theory does have significance even to a snowball melting. So I will go through and solve those and make various conclusions. In the next piece, that'll be more for 125 students and 207 students. And then I'll talk about slope fields and a little bit of theory. That will definitely be for 207 students. All right, if this is interesting to you, give me a like, give me a comment, tell me to keep going because I want to know. I'm finding this interesting to get to go back to these problems and build these resources. But I want to know it's interesting to someone else for me to continue to spend time on it. All right, thank you.